So spin-caloritronics, I think I started that word about 10 years ago for fun, as a joke basically, and Jaroslav Cerkovniak said it's a pompous word for a boring subject. But until now I think it is still live and kicking, and as you will see, there are conferences already planned for next year and the year after that as well. Now, this is the activity today. I would like to compliment Heido for finding this very nice picture of, I think it's a Danish painter called the Brennende Molen, which indeed nicely picturizes the concept that heat, the fire, and spin, the rotating rotor, that these are intertwined in this field. I would like to apologize to those who came to SpinCaloritronics 7, because there will be a large overlap between my talk now and and the one or the pedagogical in Utrecht. So I'm coming directly now from Sendai in Japan. So if I fall asleep during my talk, then I hope you understand why this is happening. For those who don't know it, I think it's the best town in Japan to live. It's not too big, not too small. It's not too busy and not too boring. There is nice sea. And there are great mountains. You can go skiing, you can go hiking, you can go cycling, and the food is excellent. I'm part of Tohoku University, and Tohoku University has some institutes. One of them is the Institute for Materials Research, which had its 100 years birthday just a couple of months ago. Okay, so now let's see, this got mixed up. This is the topic of the talk today, spin-caloritronics with Magnons. And this is the overview. And I think it is too much to cover in 1 hour. So at there's more than 1 hour. Good. Anyway, you stop me when my time is over. Okay. Now, let's start first with the material of choice if you want to study spin-caloritronics of Magnons, and that is Yttrium Iron Garnet. Yeah, you see this is a nice picture of her, and it's fair to say that many people fell in love with her recently, in the last 5 years maybe, and there are good reasons for that. For example, she has a hidden beauty, which you see in the crystal unit cell here. So this is the elementary unit cell, cubic unit cell, and the different elements are yttrium, which is a non-magnetic filled shell ion. These are these yellow dots, so they are boring in this case. The iron is 3+, so they are half-filled shells with a pretty large magnetic moment, and they are encapsulated by a lattice of oxygen ions, which form tetrahedral and octahedral sites. So the ions are hidden within these cages here. Now, the magnetic ions are strongly coupled antiferromagnetically via superexchange via the oxygen ions. So, so that means the tetrahedral and octahedral site magnetic moment is in the opposite direction. But it's not an antiferromagnet, it's a ferrimagnet, because we have more of the tetrahedral sites than the octahedral sites. And I think there's one iron moment basically per chemical site, for chemical unit. So yttrium iron garnet does not occur in nature. It's an artificial compound. and its magic is the very high quality with which it can be grown, either at single crystals, but more recently also in thin films. Now the reason for that is simply that people have worked on this for several decades. Material science is a slow science. It takes a long time before you find out how to grow material in the sufficient quality, and that's the nice thing about YIG. So we know that it is it's close to perfect, and then it's a good material to really understand the physics. So I would also like to say that YIG or YIG is the two-dimensional, high-mobility two-dimensional electron gas for magnetism. Now it's a very good electrical insulator with a large band gap. It has a very conveniently high Curie temperature. And we will see it's important that the acoustic quality of YIG is very good. So it's the same order as quartz, for example, which is used in your watches. And most important, it has a very high magnetic quality factor. So that means if you excite the magnetization, it will go on for a long time before it is being damped out. Also interesting is the large Faraday effect, but this is achieved only by doping. And if you dope it, the magnetic quality goes down. One of the challenges for materials now is to find a YIG with a large optical coupling, but still high magnetic quality. People are really eager to have such a material. So if someone of you has ideas in this direction, that would be great. Anisotropy can be also tuned. Usually pure YIG has a very, very small anisotropy. But by doping, you can get anything you like. You can also get it perpendicular, for example. So the magnetic bubble memories a long time ago, they are based on YIG with a perpendicular magnetization. Okay, the elementary excitations, as you hope, of such an insulating ferromagnet are the spin waves or magnons, which are the solutions of the linearized LLG equation. So if we forget for the moment on magnetic dipolar effects, then the spin waves, they have a dispersion, they have wavelengths, and their energy changes with wavelength or with the wave number quadratically, and this mass term here is called the exchange constant or spin wave stiffness. Now the solutions are plane waves. That means you can make linear combinations of them and generate wave packets, just like you can do with electrons, for example. Now, if I make a wave packet here in reciprocal space, then in real space, it will also, if this is Gaussian here, it will also be Gaussian in real space. Now, such a wave packet corresponds to a dip in the magnetization. The magnon is an excitation of the magnetic order parameter, which reduces the magnetization in the z direction. So this wave packet is a dip in the magnetization, and it moves with the group velocity, which is the derivative of this dispersion relation. Now, such a moving wave packet, it carries angular momentum, magnetization, it's a reduced magnetization, and also energy associated with that. Now, these magnons, if you go to low temperature, you will find that they obey Bose commutation rules. So they have the same statistics as light or phonons, which is a Planck statistics like that. And at high temperature, this goes over into something which is called the Rayleigh-Jeans distribution function, which looks like that. So YIG, as we saw, was very complicated. So that means that the simple spin waves picture we have does not hold in general. So we have to find out what is happening here. So first of all, let's consider a very simple ferrimagnet. That means that you have an ordered state of different magnetic ions which have opposite magnetization and either not exactly the same magnetization, or as in YIG is more one than of the other. Now, this majority spin, if you apply a magnetic field, is dominantly ferromagnetically coupled, and it will precess in a magnetic field, if you excite it in a magnetic field, in an anti-clockwise direction. And the fact that you have the smaller ones here, which are coupled less strongly, is not so important. However, these ones here have also a different mode. They can also precess, but they feel the antiferromagnetic coupling of the majority spins much more strongly than the applied magnetic field. So if we excite them, they will precess in the opposite direction, right? Because these here, they do not feel they feel a magnetic field just in the opposite direction. So they precess also in the opposite direction. Also, this exchange field, this antiferromagnetic exchange field, is in general much higher than the applied magnetic field, so the excitation frequency is also much higher. So we can expect in ferrimagnets two types of modes. There are the ferromagnetic modes, which precess with a magnetic field, and there are the optical modes, the antiferromagnetic modes, which precess in the opposite direction. Now, if you look at a simple ferrimagnet, like magnetite, for example here, then you see this picture confirmed. Now, the way to measure spin waves is inelastic neutron scattering, because the neutrons, they see the magnetic field, and they can see the dynamic magnetic field, so they can pick up or excite a magnon, and you can do this as a function of the scattering angles and map the whole spin wave band structure. And here you see some very old results from 1962. Now we see there is a nicely almost parabolic dispersion, which corresponds to this ferromagnetic acoustic magnons, and the optical magnons here, they are at a much higher frequency. And this delta here is the exchange energy, this exchange splitting. Now, if you look at KT, which governs or which shows you how much of these magnons are occupied, according to the Planck distribution function, then you see that's about here. Now, the spin wave dispersion up to these energies is roughly parabolic. So for all properties of magnetite at room temperature, you can completely forget about the optical magnons. It behaves like a very nice ferromagnet. Now, YIG is a little bit more complicated, and you cannot do this simply analytically anymore. So one way to do it is to find out what's really happening here is our atomistic spin simulations. And we have an expert here in the audience. So if I say something wrong, then she will correct me, I hope. So what is this method? It's basically a classical method in which you have classical spins sort of on the positions on the lattice, which follow the conventional equation of motions of classical spins, of classical magnetic moments, which is the Landau-Lifshitz equation. But it is also damped. There's also always viscous damping. And this can be conventionally is described by this Gilbert damping term alpha. So this really looks exactly like the macrospin Landau-Lifshitz-Gilbert equation, but is now assumed to hold for each spin individually. Now, the effective magnetic field in which these spins move consists not only of the applied magnetic field, but also of the exchange field of the neighboring spins, which are also moving. Now, this effective field here is time dependent if everything is moving. Now, if we have damping, then we know by the fluctuation dissipation theorem that we also have noise. And this noise is usually modeled in terms of a random magnetic field, which is in the classical limit correlated like that. So this means this is the correlation of these random magnetic fields, which each ion fields, is scaled like that. So it is proportional to the temperature on the lattice psi t and this damping constant alpha. So if we increase the temperature, the noise the spins feel will also increase. So we assume now that all the temperatures are the same in order to get the equilibrium properties of the system. Now the parameters here, they are pretty well known from high precision neutron scattering experiments. Now what Joe Barker in Sendai does is he simply solves by brute force this equation of motion, coupled equation of motion for each spin in a very large cluster. The result of it is a time row, is an S of t, a very large array of these spins for small time steps over a certain time interval. So this huge data set can be analyzed, and usually it is done by calculating the correlation functions of these spins and Fourier transforming them. And then you find singularities in the spectrum, which corresponds to the spin waves. Now here you see the results of such calculations as a function of temperature. Now the temperature comes into this calculations only via the random magnetic fields, because they scale as the temperature. For the rest, all the parameters are all the same for all temperatures. Okay, so you see a very complicated band structure, which is just like in electronic band structures. We know that if the material gets more complicated, the band structure gets more complicated. If you have a periodic system in reciprocal space, you have to define the corresponding Brillouin zone, and you get the different bands there, which goes to the band edge here in different directions, and it's really a board of spaghettis. What you also can do is you can look at the sense of the precession of these spin waves, and this is indicated here in these color codes, where the red one is the ferromagnetic precession, the ferromagnetic modes, ferromagnetic spin waves, and the blue ones are the optical ones, the anti-ferromagnetic ones. So this is at low temperatures, and you see very sharp lines, very sharp spin waves, which actually agree very well if you take a very simple Hamiltonian, spin Hamiltonian, and diagonalize that one. But what you see now, if you increase the temperature, you see two things. First of all, some of these bands, they get broadened. That means the lifetime of the spin waves goes down, and the reason for that is nonlinearity in the system. So they get higher excited, they get larger amplitudes, and then they start to interact, which is Magnon-Magnon scattering. And this reduces the lifetime, and these become broadened and broadened, more broadened. What we also see is that the exchange magnon here, this is going down with temperature. Now that reason is also quite easy to understand, because these antiferromagnetic ones, they precess in the exchange potential of the majority spins. With higher temperature, the magnetization goes down, and this exchange potential also goes down. And it turns out that it goes down so strongly that at room temperature, these antiferromagnetic modes are occupied. Now here you see this band gap here, this difference between the acoustic and the optical ones as a function of temperature. And you can compare it with neutron scattering data here, and the agreement is very nice. And you see around room temperature there is this crossing. So if you look for temperatures, if you really want to describe the properties of Yig at room temperature, you should take into account the antiferromagnetic modes. At low temperatures, however, here we see, I think, the simple ferromagnetic quadratic dispersion for this exchange mode is perfectly all right. Good. Next topic I would like to discuss is the mixture of these magnonic modes of the spin waves with other excitations of the system. This can create hybridized states like this liger here. It's a hybrid of the tiger and the lion, right? Now the standard example of such a hybrid state is the so-called Magnon-polariton. So if we excite a ferromagnet with a microwave, then this microwave has an electric component and a magnetic field component. And the magnetic field component interacts via the conventional Zeeman type of interaction with the magnetic order parameter. Now, if the frequency of this magnetic field agrees with the natural frequency of the excitations in the ferromagnet, then something interesting happens. First of all, the interaction between these two modes, that gives you matrix elements, interaction matrix elements. In perturbation theory, then say, okay, you have this matrix element squared divided by the energy difference. Now this works nicely until the frequencies, natural frequencies, cross. Then you get an interaction between these modes, and this gives you a so-called anti-crossing. So a photon has a linear dispersion, and the frequency is linear with k, and the light velocity is this one here. So this is a very steep one. The magnons, they have a quadratic dispersion, but on this very small wavelength where this cross, it's basically just a line. And here you have this, this anti-crossing. Now the fact, and if the broadening of the system is smaller than this anti-crossing, then you say we are in the strong coupling regime. If you do ferromagnetic resonance, you will see that your ferromagnetic resonance peak is not just one peak, but it splits into two. And this has been observed by many groups now for Yig in cavities or also not in cavities. Now there's another elementary excitation of the system, which are the phonons. And these I would like to discuss now. Oh yeah, by the way, here, in this regime here, we do not have a magnon and a photon anymore. We have a mixed state which oscillates between being a magnon and a photon. It's a hybridized state, and this is usually called a Magnon-polariton. Okay. Now, the spins can also interact with the lattice. Now, we know that we have magnetic anisotropy. That means that the magnetization is usually locked to the crystal lattice. So if you deform your lattice, then the magnetization would like to follow this lattice. These two order parameters are coupled. Now this coupling gives you the magnetostriction, for example, if you are in the DC limit. But the dynamics, when everything starts to oscillate, there are also effects, of course, because if you excite the lattice, magnetization would like to follow, and vice versa. Now, different phenomena this gives rise to different phenomena. For example, the thermalization of the lattice and the magnetizations is a consequence. The fact that there is a Magnon-phonon drift, that you can sort of increase the Magnon transport by the phonons. This is another one. And also for these Magnons and phonons, they are hybridized states. And these have already predicted a long time ago by Kittel. Now if you want to calculate that, then you can transform the system into a set of, at least at low excitations, into a set of harmonic oscillators. Sort of, we know phonons are harmonic oscillators, magnons are harmonic oscillators, but by this interaction, by the magnetoelastic interaction, these two are now becoming coupled. So we have coupled oscillators and with some coupling constant, which is very, very well known, in fact. Now here's a plot which has been made by Akash on a logarithmic scale. You see here the phonon distribution, the phonon dispersion, which is just again a linear curve, and the slope of this curve is the sound velocity. Now there's a magnon which is parabolic, and this can cross this magnon curve at some point. Now on this scale you don't see anything, but if you sort of blow it up, you will see something which looks very similar to what we have seen before. Now in the case of the photon, it is called a Magnon-polariton, and we choose to call this hybridized state a Magnon-polaron. So although this is a little bit, the polaron has also a different meaning, but I think if we say Magnon-polaron, it should be quite clear. So how can we see whether these Magnon-polarons exist? And there's a very nice optical technique which has been able to do just that, and this is spatiotemporally resolved pump probe spectroscopy. So what these people basically do is they throw a stone into some pond and observe how the waves emanate from this excitation source. So you hit with a focus laser, you hit your film, in this case it's a YIG film, and with another laser, making use of the Faraday or Kerr effect, you measure the magnetization. Now, without anything, the magnetization is in plane, and the Kerr effect only sees the magnetization normal to the plane. So you don't see anything at rest, but if you excite the system, it starts to precess, right? That means you get up and down magnetizations, and this can be resolved like a sort of stroboscopically and also as a function of position. And this is a three-dimensional picture of what the people measure here after some time, after a few nanoseconds. This is where they hit the sample. You see something is still oscillating there, and you see that waves are emanating just like from the stone which you throw into the pond. Now, how can we understand that? Now, we know what the equations of motions are, the LLG equations for the magnetization. Now, if you use the LLG equations, you will find that you cannot explain whatsoever what's happening here. The LLG equation is not enough, but the situation changes if you take into account the interaction of the magnons with the phonons. And again, these equations in the linearized regime are very well known, but to calculate them is not so trivial, and this has been done by Kashen from Delft. So I will not go into too much technical details, just show you here the comparison between theory and experiment. So this is a snapshot of the magnetic profile after 3.45 and 6.2 nanoseconds. So at t equals 0, we excite it at the center, and look how the magnetization propagates. Now this one is the theory, and these ones are the experiments, and we see that there is quite a good agreement. Now what is interesting is that we see that we have basically, so first of all there's still something remaining in the center, and we see two rings. Now the inner ring here is sort of has a different symmetry than the outer ring. And we can understand this perfectly well by noting that the radius of the ring, which is a direct measure of a velocity, right? You're waiting 6 nanoseconds, and how far did it go? Now this radius corresponds to the inner one, to the velocity of the transverse, the shear phonons, transverse acoustic, and the other one, the longitudinal acoustic phonons. Right? So what we see here is that magnetization is transported with the velocity of the phonons. The velocity of the magnons itself on this length scale is much too small. The magnons are in general very slow. They would just, on this scale, would still be centered here. So something is what is happening here. To explain the system, it is essential to take into account Magnon-polarons. Magnon-polarons, they are magnetic, they carry a magnetic component, but they move as fast as the phonons. And the interaction between the transverse and the shear waves and the pressure waves is different, has a different symmetry, and this you see here. Now, the agreement with experiment is really very nice, and this also goes for magnetic field dependence and so forth. So what you see here are not magnons, what you're seeing here are Magnon-polarons. And we can also conclude that they are excited not by some magnetic field, which is carried by the laser, but it's carried by the heat. So at T equals 0, we are heating our system. We are heating the phonons, right? And the phonons then relax, and when they expand, they, by the interaction, they take on the magnetization and transport. Good. Okay. Next topic I would like to discuss is the topic of quasi-equilibrium states in spintronics, which is also important for spin-caloritronics. So let's go back to maybe the most elementary concept in spintronics, namely that of spin injection. Now this is usually done in heterostructures, which consist of a ferromagnetic metal and a normal metal. Now we know quite well that transport in ferromagnets can be explained nicely in terms of the two-channel model. Namely, they have the upspin electrons and the downspin electrons, which are, to good approximation, independent. And the electric resistance of these two channels is different. In a normal metal, of course, up and down are equivalent, and the electric resistance of these two spin species is the same. So such a heterostructure can usually be modeled by an equivalent circuit, as indicated here. So what happens if we close the switch? Then the currents, the electrons, will prefer to take this path of lowest resistance, which in this case is the upper one. So there is now a larger current of the upspins flowing into the normal metal than the current of the downspin. Now this gives an imbalance in the spin population in the normal metal, right? It becomes magnetic, as indicated by the red color. But it is a non-equilibrium state with a certain lifetime, which is given by the spin flip length and spin flip time and a certain length scale, the spin flip diffusion length. Now this magnetization here is, this non-equilibrium magnetization is called a spin accumulation. Right? So it's usually measured in terms of the chemical potential of the upspins and the downspins, which in this non-equilibrium state are different, like indicated here. Now this spin accumulation has been around for a long time, but actually it is difficult to measure. It's only last year that people have really succeeded in seeing the spin accumulation directly by a technique called XMCD. So this is the absorption of X-rays for right and left polarized radiation. And if the system is magnetic, you see a difference. And you can do this element specific. So in these experiments, you see here there is a spin valve, gold, copper, and here is the magnet, copper, nickel, palladium, and this is again a non-magnet. And people just look at the transmission of these X-rays, and they look exactly at the copper absorption edge. And if you see a difference between the right and left circular photons, then you know you have a magnetization. And people see this magnetization only if you drive a current through the system. So it's a direct measurement of the spin accumulation, and as indicated here. Now this was done by the Stanford collaboration. The Berkeley collaboration had some problems with the referees, but this also appeared very recently. Now just because we are with spin-caloritronics here, I would like to show you another experiment which is a proof of this existence of the spin accumulation, which was carried out by my colleague Da-Si Ho in Sendai. So these are the experiments. Here they have a thin film of gold, right, on top of Yig. Right. So, and now I think I will discuss this a little bit later. But they also apply a temperature gradient on this system. Now, in this system, in this configuration, this is called the spin-Seebeck effect, and we will discuss later that in this spin-Seebeck effect, the spin current is flowing from the ferromagnet into the normal metal. Now, usually, this spin current is then measured by the spin-Hall effect. But that's not a direct proof that there is a spin accumulation. Now, Da-Si tried something different. He used a configuration in which there is no spin-Hall effect, namely by applying a magnetic field normal to the plane. So the magnetization of Yig is now pulling out of the plane. So there's no spin-Hall effect in this case. But what can happen now? Now, if it's really true that we are injecting a spin accumulation into this gold, as I said, we would magnetize gold, right? So it should become a magnet. Now, how can you find out that something is a magnet? Now, you have to show that time reversal symmetry is broken. And the best way to do it is to measure the so-called anomalous Hall effect. It's an Hall effect which basically exists without the conventional Hall effect. Now, this is exactly what Da-Si has been measuring here. So, under the conditions that there is a finite gradient, he is getting a probe current through the gold, and he measures indeed a Hall signal. He measures an anomalous Hall effect in gold, which is not magnetic in equilibrium. Now, this is a direct proof of the spin accumulation. Now, here's the experimental result, in which he sort of shows that if you are reverting the magnetic field, indeed the signal also changes sign. And is also not going linear through, it just becomes constant here. There's no effect at zero magnetic field, so there is no something like an equilibrium proximity effect either. Now, there's a similar experiment he is doing here with spin pumping, but that's not so important at this point. If you analyze these experiments, you get a parameter out of it, which looks like this one, which is this anomalous Hall resistance, can be written in terms of the spin accumulation μs, and the derivative of the spin-Hall conductivity. Now, this spin-Hall conductivity, this derivative, is very closely related to something which is called the spin-Nernst effect. Now, in order to complete the story, let me just show some experiments which indeed also show that there is a spin-Nernst effect in platinum in this case. Now, where is it now? Oh. This one, yes. So what's the spin-Nernst effect? The spin-Hall effect is defined like that, right? So you're driving a charge current through your conductor, and you will get a transverse spin current. And the coefficients here between these two is the so-called spin-Hall angle, right? Now, what's the spin-Nernst effect? It is per definition defined like that. So this one would be the charge current, which is driven by a voltage difference, assuming that the temperatures are constant. Now, if you drive a charge current through the system purely thermoelectrically, right, by a temperature gradient, then you also get a charge current, and this charge current also generates a transverse spin current. And this angle here, this coefficient, is called the spin-Nernst effect, spin-Nernst angle. Now, how can you measure that? Now, this is the structure here. So it's a whole bar structure of platinum film on top of YIG again. On the left side, you see there is a heater. So by driving a current to this one here, this gets hot. Now, if this gets hot, then there will be a temperature difference between this contact here and this contact. This means there is a heat current, and if you have thermoelectric effects, also a charge current is flowing from here to here. And these are Hall bars, which can measure the Hall effect if you like, but they actually measure it differently, making use of something which is called the spin-Hall magnetoresistance, because the spin current which is induced is in this case directed normal to the current direction, and as a function of the magnetization of the YIG below, it can be absorbed or reflected. And this modulation can be used to get the spin-Hall angle if the charge current is induced by voltage. But it can also be used for this temperature difference to get this spin-Nernst angle. So by analyzing these type of experiments, we find that the result for this ratio of the spin-Hall effect and the spin-Nernst effect is indicated as minus 0.5. So the spin-Nernst angle is twice as large as the spin-Hall angle, and it has a different sign. Right. So, yeah, and there have been band structure calculations by Gerrit et al. From the Ebert group, which find also that the sign is different and the magnitude is in pretty good agreement. Good. So, what's the spin accumulation? Again, we have a diffuse system, right? That's all what we assume. These metals, they are diffuse systems, and there are all sorts of scattering processes going on. Now, these scattering processes can be classified as being spin conserving or spin flip. Spin conserving processes is scattering at a normal impurity. So an upspin electron hits an impurity and is scattered without losing its spin. These electrons, they can also scatter at phonons, right? But phonons have usually energy, so that means while here the energy this is elastic scattering, here the energy changes. There's also electron-electron interaction. And they can be classified. In this case, a spin is always conserved, right? Because, yeah, that's a question of symmetry. But there can be a direct scattering in which the incoming electron keeps the spins, or there's exchange scattering where the spin is exchanged. Now, these scattering processes, they create diffusion. That means an electron is not going ballistically one side to the other. It is just scattered like in a flipper game or so many times, and it becomes diffuse. But there's also energy exchange with different systems. So there's also thermalization. So if we have hot electrons and cold phonons, by the electron-phonon interaction, they're able to exchange energy, and depending on how efficient you're scattering, at sometimes the temperatures will be the same. So there's also thermalization between the up and down spin electrons. But these scattering processes, they do not destroy any spin information. In order to do that, you need spin flip scattering, like magnetic impurities or spin orbit impurities. There's also spin flip scattering at phonons if you have spin orbit interaction, and in ferromagnets also with magnons. Now the point is that these processes in most systems are weak. Spin-orbit interaction is usually a weak process. It's much smaller than all the other scatterings. Now, and this you usually invoke in order to define the spin accumulation, right? So you're exciting the system, you're driving some spins into the system, and we assume that they diffuse quickly. So that means that we can talk about a quasi-equilibrium state, and they are also exchanging energy with the environment quickly. So the electron temperatures and the phonon temperatures get the same very quickly as well. Now, in this case, in this assumption, such an electron distribution looks like, if you have a parabolic band structure, you say, okay, they are filled by a Fermi-Dirac distribution function with a certain temperature, assuming thermalization. And this distribution function can now change as a function of position, but very slowly. Now, as you see here, this example here, we see that the temperature of the down spins is higher than the temperature of the upspin electrons. Now, this we call a spin-heat accumulation. Now, whether this exists or not is a bit complicated. Experimentally, it has been proven basically that it exists. And these are experiments which have been carried out in the group by Van Wees and Groningen. It's a rather complicated three-dimensional structure, and you see a sketch here. Now, the essential element here is a spin valve, F and F here. And what these experiments show is that the heat conductivity of this spin valve is different when the magnetization is parallel and antiparallel. Now, purely for the charge current, this would be just a conventional spin valve effect, and which basically proves that there is a spin accumulation in the normal metal. Now, these experiments show that there is a difference in the heat conductance, which means that this is a proof that there is a heat accumulation in the normal metal here. Now, these are the traces, the experimental traces. This is the magnetic field, which switches the spin valve from parallel to antiparallel. And we see basically here that the heat conductivity, heat conductance of the spin valve is different for the two configurations. Now, if you make the normal metal layer thicker and thicker and thicker, the signal becomes smaller, and from that you can derive a spin relaxation length for the heat, which is pretty long. It's 60 nanometers in copper at room temperature, and even longer at lower temperatures. So actually this is a very funny result, because theoretically there's not a real reason why a spin temperature should exist. Because we know that by the electron-phonon scattering, there should be no, that would thermalize the upspin electrons exactly the same way as the downspin electrons. And for the electron-electron scattering, the difference is not so large. Time really flies, right? Actually, this distribution, which you inject into a normal metal by transport, can also be measured directly at low temperatures in these old experiments. What you see here is tunnel junctions to a normal metal, and these ones here are superconductors. By tuning the voltage level of the superconductors, because they have this very sharp edge for quasi-particle transport, they can really measure the distribution functions of the electrons in the normal metal at these positions here. And as a function of the delta U over this bridge here, they do not see something which is close to a Fermi-Dirac distribution function. No, they see a double step potential of electrons which come from this side and electrons which come from that side. So there is not a thermalized distribution in the system. So that means the whole concept of the spin accumulation in terms of Fermi-Dirac distributions is something which is absolutely not rigorous. So what we should do is we should assume that these temperatures, these parameters, are some sort of a parameterization of something which might look very different. For example, if you look at this curve, for example, right, you could say, okay, let's describe it by a Fermi-Dirac distribution function which looks like that. It does not have this double step, but it sort of effectively describes this smearing out of the distribution function. And we can take that as an effective temperature. Exactly the same we should assume with this electron distribution function. We do not know how they are distributed, but we can parameterize them by some efficient broadening and center of the Fermi-Dirac distribution function. Okay, yeah. Very quickly, you can do the same for Magnons.
You have more time.
Pardon me?
You have more time.
I have more time?
Yeah, till 10:30.
Tot?
10:30.
Oh, I still have an hour. Okay. Oh, okay, that's okay, good. Really? Oh, yes, you're right. Yeah. Okay, so let's go to the Magnon systems then. We can have exactly the same story as mentioned now, right? You can sort of excite your system, your Magnon system. You can excite it by light. You can excite it electrically as you like. So what will happen? Now, there will be scattering processes, right? So there are impurities which will scatter the Magnons. These are elastic impurities. The Magnon energy will not change. But there's also interaction with phonons. Now, in general, the Magnon scatters into another Magnon. That means that basically spin is conserved. But energy is not conserved. No, there's energy can go from the Magnons into the phonons or in the opposite direction. So this process will thermalize the Magnons and the phonons with each other. Now, this one here is another scattering process, right? There's a Magnon is not absorbed, but a Magnon is scattered, and the phonon is also scattered. This, again, will the same. It will correspond to diffusion of the Magnons and also energy exchange. Now, then there is Magnon scattering, which also sort of thermalizes the Magnon distribution. Now, these are all Magnon-conserving, spin-conserving scattering processes. But there are also non-spin-conserving scattering processes in which the Magnons lose their spin, right? So this can, for example, if you come in with a Magnon and you emit a phonon, for example, then the magnetic system loses angular momentum. This can be also written as a scattering process like that. So there is a Magnon is lost. Now there are also processes, 3 Magnon processes, where you come in with 2 Magnons and they merge into a single Magnon, which also corresponds to angular momentum loss. Now all these scattering processes, they involve the spin-orbit interaction, and they are therefore much weaker. It depends, of course, on the material. But we know that in YIG, this damping parameter alpha, which is just the loss of angular momentum, right? The magnetization dynamics is damped, which means angular momentum is lost or gained, as you would like to call it. So this is in YIG, it's proportional, somehow proportional related to alpha, and alpha, in this case, is very small. So it's quite safe to say that all these processes are sort of a perturbation. We first consider these processes here in order to find out what happens to a non-equilibrium state, and this one is a correction to that. Okay, so how does this work? Here is a plot of this Fermi-Dirac distribution function. Not Fermi-Dirac, this is now a Planck distribution function. And actually, with the chemical potential, it is a Bose-Einstein distribution function. Now let's first assume that, and this is the case for equilibrium. So magnons are energies like phonons and photons. The chemical potential at equilibrium is always 0. So if we have a Magnon system at equilibrium, at finite temperature, we have a distribution function which looks like that. That's the black one. Now let's assume that we are somewhere sort of exciting our system. So we are exciting a distribution of very hot Magnons. So what's going to happen? Now first of all, we assume that only the Magnon conserving processes are relevant on the fast timescales. So that means that if we have hot Magnons on top of cold phonons, right, there will be an energy exchange between the phonons and the Magnon system. So the phonons will maybe get a little bit warmer, but the Magnons will get colder. Right. So that means we get a distribution function which goes from here to this one here. Now, yeah. So now, first of all, now let's see once again. First of all, let's assume that we excite it, and let's first assume that the Magnons itself thermalize, that the Magnon-Magnon scattering process are most efficient. In that case, an initially non-equilibrium distribution function will become a Planck distribution function like that. Okay, but this is sort of still not a very satisfactory state because this one is the equilibrium one for a large temperature, but the temperature between the Magnons and the phonons is still different. So the Magnons would like to lose their energy, transfer the energy to the cold phonons, but this is not possible if we assume that things are thermalized according to the Planck distribution function. Right? So the hot Magnons still would like to lose their energy. So the only way to realize something like that is to change the form of the distribution function. And one way to do that is to introduce the Magnon chemical potential. So assume that this is not 0 anymore, but it becomes a little bit larger than 0. Now, if we do that and sort of assume that you have include this mu for larger 0, but still keep, and then sort of, by now how was it? If we take mu equals larger than 0 and allow T to become the phonon temperature, that we allow the Magnons to lose their energy to the phonons, but change the distribution function according to a certain mu, you get a distribution function like this green one here. Clearly, the total energy of this system here, which is now at equal temperature with the phonons, but has a different distribution function, is more favorable than the one before. And we see there's quite a deformation now. By the chemical potential, we are allowing to have more Magnons close to the band edge than we would allow in the conventional Planck distribution function. Now, actually, there is no microscopic reason why it should look like that. It's just a way to parameterize the distribution function and sort of to allow something which looks like a quasi-equilibrium state. So the situation is quite similar to the one of the spin accumulation in metals. We do not really know that we can describe them by Fermi-Dirac distribution function with a certain temperature, but we can parameterize it this way. So clearly, this is an effective way to do that, and this chemical potential mu is a parameter which we can use to describe the experiments. And it describes a deformation of this distribution function from an equilibrium one. Now, this chemical potential is, of course, something which we know from massive Bose particles, right? But it's complicated, it's more complicated in magnons because they are basically pure energy. So at equilibrium, we know that we have a distribution function which looks like that, and this is the Magnon number. Now, we also know that this is a really quantum distribution function in a certain, if the sort of the Thomas, the Broglie thermal length is larger than the inter-Magnon distance, right? So if this one here is larger than this parameter here, we know that the magnons overlap and we can expect quantum effects. Now the point is that this description does not work anymore if you pump the system. So you can inject additional Magnon systems, magnons, without extra energy, because this can relax easily to the phonons, which is larger than this density of equilibrium states. Now, if this is the case, then we can describe this new system, this new non-equilibrium system, where it's more magnons than we can usually can handle by equilibrium statistics, by getting this chemical potential here. Now, the interesting thing is now that if this chemical potential approaches the band gap of the magnons, so that is this omega 0, then even this distribution cannot take care of all the Magnon states, and then we get something which is a condensate. So Magnon condensate is a coherent state of the magnons at the minimum energy of the system. Now, you can get sort of a criterion for that if you assume that the magnons are non-interacting. Now, this topic now of whether or not you can have Magnon condensation and what the properties are of this condensate is a very popular one at the moment. So it's possible to get a large number of magnons into a Magnon gas by parametric pumping with strong microwaves, and this has been done in Münster and in Kaiserslautern, for example. And it would be very nice if we could create this type of condensates also electrically. And that is where many people are working on at the moment. Good. So let's then go to from this general discussions to Magnon transport, and then specifically spin-Seebeck effect. As I mentioned before, the spin-Seebeck effect is the creation of an thermoelectric voltage by a temperature gradient. The sample usually consists of an insulator like Yig and a heavy normal metal like platinum. And we assume that there is a temperature gradient over the system. Usually there are three processes involved. Directly at the interface, you have a process which is called the balance between spin pumping and spin transfer torque at this interface here. Then, so this would then inject this net spin current into the normal metal. Next, there is the transformation of the spin current, which has been injected into the normal metal, into a voltage by the inverse spin Hall effect. Finally, there is the fact that the magnons, if they are depleted here at this point, they have to be filled from the bulk. So there's also spin current generation and spin-Seebeck effect from the bulk itself. And all these processes are important to describe what is happening here. Now, I will now not discuss too much about what is happening here exactly, but the point is that if the temperature gradient in the bulk is larger than the temperature gradient which you have at the interface, this process, what happened here in the bulk, is very important. Furthermore, usually this one here is an atomistic process, which is not strongly temperature dependent or magnetic field dependent. So in many processes, in many experiments, you can basically forget about what's happening on the right side and interpret the spin hole voltages as a function of some parameter as something which has happened in the bulk. And I would like to discuss two recent examples. One has been, I think, it's a collaboration between the experimental groups of Mainz, Kaiserslautern, I think München, and Sendai, actually. And these have been carried out by a very interesting material class, which are the rare earth substituted iron garnets. So as mentioned before, yttrium iron garnet, the yttrium itself is boring, it does do nothing. But it is possible to substitute this yttrium by a rare earth ion with a magnetic moment. And then things get complicated and interesting. So here you see, for example, and these are very old experiments actually, the magnetization of these rare earth substituted iron garnets. And this one here would be the YIG, right? This is just a very boring type of mean field magnetization. But the interesting thing is that if you replace this by other ones, you get curves at which the magnetization vanishes at some point. In this case, there is a cancellation between the magnetization due to the rare earth ions and the magnetization due to the iron. And these are called compensation points. I will not go into the details. I just like to show you very briefly the experimental results of this paper here. Now, these are the experiments of the magnetization which show this nice dip at the compensation point, which is well known. And this one here is the spin-Seebeck effect under the same conditions. Now, the interesting thing is that it changes sign not only at the compensation point, but also at the second point. I show you this because it indicates that the spin-Seebeck effect can be used as an instrument to understand spin correlations in the magnetic system you are interested in. So this one here can actually be easily explained. It has already predicted before by the Maekawa group. This one came as a surprise. So I think these are really magnificent experiments. I don't really understand why the referees didn't like that so much. In hindsight, we could explain this in terms of the strong temperature dependence of this exchange constant we have seen before in YIG, but which has more direct consequences for the spin-Seebeck effect for this gadolinium iron garnet. And if you want to understand the details, please look up this paper. Next, I would like to discuss this quite recent experiments, which were carried out in the Saito group in Sendai. So I think half a year ago, Professor Saito came to my room and said that he found this strange results in the spin-Seebeck effect, and whether we had any idea. So this is an example of the plot that this is the magnetic field. Now, if you change the magnetic field and the magnetization, it's quite obvious that you expect a change of the sign of the spin-Seebeck effect. So this goes very nicely like a step function and then is constant. But on top of these signals, you see these little peaks. And they were completely reproducible. So in the beginning, the experimentalists themselves thought that it was some glitch that somehow the magnetic field was not stable. I don't know what, but it comes back, and you see it in all different types of samples. So what could this be? Right. Actually, I have tried to prepare you already for that, but these are caused by the Magnon-phonon, which we discussed before already. So, as mentioned before, right, we have the Magnons, which have roughly parabolic dispersion, plus, of course, the deformations due to magnetic dipolar forces, but that's not so important. Then we have the phonons, and there are just two phonons. There are the pressure waves, the longitudinal phonons, right, which have a higher sound velocity than the transverse ones. Now this is K, and we see that under conventional fields of about 1 Tesla, there are crossings, in this case, with the transverse phonons and also the longitudinal phonons. Now then we know that we have the magnetoelastic coupling, so these phonons are coupled with each other, and they can have crossings or anti-crossings at these points, right? So now this is a different scale than we've seen before, right? In the beginning, if we did these optical experiments, we were sort of did not have to consider, we had to consider K states only, which are sort of reachable by the width of the laser spot. So that was limited to this very small region here. Now we sort of can consider thermal excitations at different temperatures, and then we have to consider the whole of the phase space. Now here you have these crossings of these states. Now, how can you now sort of try to understand what is happening here? Now, the easiest way to do, so what we want to do here is we want to understand the Magnon transport under thermal gradient. And we assume that these peaks now are not coming from the interface because we do not know any process which could cause that. We assume that that is simply constant for the parameters we are considering. So we can just consider bulk transport of magnons in the ferromagnet, and this is governed by a so-called Boltzmann equation, and we can simplify it, we can linearize it, and we can make an approximation which is called the relaxation time approximation. So the time dependence of the distribution function sort of, this is the Boltzmann equation. This is the time dependence, right? This is the gradient in space, and this one here is the group velocity. Now all these parameters we know. So we know them for the magnons, we know them for the phonons, but we also know them for these combined systems of magnon and phonons. So these parameters I and K now describe the band and the wave vector. So at a certain K, we have then 1, 2, 3 different bands to consider. Now, again, the solution of this is complicated and has to be done numerically. Okay, so so we have now to take into account, of course, in order, if we want to see any difference, right? We see a difference if we want to, if we claim that it's are the phonons what we're seeing here, it must come from these interaction regions here, this point where there's Magnon polarons, and we have 4 of them in this case. First of all, they must be occupied, right? Which gives you some ideas on what type of temperatures you are in. So if we have low temperatures, we have a distribution function like that, and in that case, we can, for example, forget about these ones here. They would not be occupied. At higher temperatures, we would expect that this becomes more important. So there is a clear temperature dependence we have to explain. Here are sort of some results. at a certain temperature here. And these are the calculated results with the background and on top of that. And we find that have the enhancement here, the small enhancement, always when the magnon and the phonons touch. Okay, so here is a crossing point, and this would be a touching point. The difference between these is that here the number of k-states which contribute is small. Here the number of k-space where things are parallel is large. So we expect the maximum effect of this Magnon-phonons here at these touching points and not at the crossing points. There's enhancement at the crossing point, but it really becomes larger at the touching point. Now what happens exactly at these touching points? The magnons becoming magnon-polarons. And whether they improve or decrease the transport, the spin-Seebeck effect, depends on the scattering. We have one important parameter in these equations, which is the relative quality of the phonon transport versus the magnon transport. If the phonon transport is better than the magnon transport, we expect an enhancement of the signal, and otherwise we expect a depression of the signal. Now the fact that we always see in the experiments an enhancement of the system, here we see a comparison for different temperatures and for different points. It is a very strong indication that the acoustic quality of YIG is better than the magnetic quality. Now this is something which can be tested because we can selectively decrease the magnetic quality relative to the acoustic quality, for example. And these are experiments which are going on. I think the nice thing is that, again, these type of experiments show that you can get information out of a magnet, an insulating magnet, by the spin-Seebeck effect, which you could not get by other ways. Good, and I think my time is up here, so I skip all the rest. See, I had a lot. These are the messages. So there's a difference between ferrimagnets and ferromagnets. In YIG, we can realize a strong coupling between the magnons and the phonons, and it can really be observed. Phonons can be important not only in sort of optical experiments, but also in transport experiments, as we have seen. Now, I introduced the Magnon chemical potential as a parameter to describe a non-equilibrium Magnon distribution, but I had no time to discuss the experiments which sort of support this idea. But you see here this conclusion of that. Thank you very much for your attention.